Hello, friends. This is a video on the curvature of quantum wave functions and how to look at them from a conceptual perspective, but also doing the math as well and showing how you get the same thing. So the whole point of a wave function is this, is that the wave function, which is definitely dependent on position, but may or may not be dependent on time, but I'll include it there anyway. We're actually going to study stationary wave functions that don't evolve in time. We're going to do what are called time independent, but that's okay. The point is, this has no physical meaning. It gives information or contains information. It is used as a mathematical tool. Often it actually uses complex numbers. If you've heard of complex numbers, the square root of -1 is involved. You get functions like this. This would be great if we could get this far, but I would have to teach you guys complex numbers and Taylor expansion. The point is, this is a mathematical tool that works, that spits out, right? It spits out or it reveals specific quantities, such as the energy, such as the momentum, such as the position, etc., right? About a particle or whatever the wave function is representing. We're going to be having them represent particles, of course. It's kind of this of course, but it begs the question, what else can we represent with wave functions? And sometimes you get like, well, is the entire universe representable by a wave function, or a human body, or a molecule even? There's definitely molecular wave functions, but yeah, we're just going to say of a particle in this class. Great. So step one is that the amplitude squared, or what you would do is you'd say this times its complex conjugate if you were in the complex phase, but you just take it and square it. You get the probability per unit length that it exists in a certain space. So we're going to want to graph psi squared of x and get like certain functions and saying, okay, it's most likely here. Because the whole point is that, like, in the classical worldview, so let's talk about a free particle. A free particle has no forces acting on it, right? So in a classical worldview, I have a particle. It's like a little ball. It's moving at some speed v, and an object in motion stays in motion. It's constant, such that its position at any point in time is v times t, plus whatever initial position I started at. Its velocity times time is v, right? Whatever it is. And even if it was under some certain force, I could determine its position and velocity at any given. So these are known. V, x, its momentum equals mv, its energy equals 1/2 mv squared, its kinetic energy equals mv squared, right? These are all known. precisely, right? But in the quantum worldview of the wave function, everything is probabilities, meaning the wave function just exists. And from the wave function, there's a probability that it has a certain momentum. So there's also a probability function, right? Saying, well, it could have this probability, sorry, a momentum wave function, or it could have this momentum, or 25% chance it has this momentum. And it's like, it's just a different world view of saying everything, position, momentum, energy, these are now based on probability. Where there are specific values that these can have, and the wave function contains that information, but typically as a, well, it's a percentage chance, right? So these are typically unknown. So for instance, you might be able to discern one of these, but if you discern one of these, you have to sacrifice information for another one. And this is called the uncertainty principle, which I covered in my other video. Because remember, the uncertainty principle said that if I have a localized wave where I know X, then the momentum is many values of the wave number. It's a spread. So delta X times delta P has to be greater than this number, H bar over 2, right? So this whole idea of probability, that nothing is known for certain, and if you know one thing, you don't know other things. That's a completely different way of looking at the universe. Completely different. No longer do we have an object and no longer do we know where it is. We just know the spread. So the goal is this, that the wave function is determined by the potential energy. What is potential energy? Potential energy, if you remember, is force times x. It's technically, in calculus, the integral, negative the integral of f of x dx, or f of r dr, whatever, f of y dy, whatever variable you're in, but I'll just choose x as a general position variable. This just means sum, like an infinite sum of all the pieces, but it's essentially the average force times the distance. For instance, gravity, which is the example I'm going to use today. Potential energy is mg times the variable y, where we'll have y equals 0 be the ground, and like y equals h be some height. I drop a ball, it falls. Here the potential energy is mgh. Here the potential energy is 0. It's a constant force times a distance. That's how you get that equation. So what is the wave function of a ball falling to the ground? Right? What is the wave function as a function of y of this? Well, here's how you figure this out. So how it works, right, is that kinetic energy is proportional to the curvature. And kinetic energy is given by the formula negative, that's really important, h bar squared over 2m times the curvature of the wave function divided by the wave function itself. So it's not 1/2 mv squared anymore, although we can use this to convert this into a velocity, but we realize that there's nothing really moving anymore. That this particle isn't moving. It's just like it could be anywhere at once. Like, for instance, instead of seeing this as moving to the ground, we could see this as spending more time here and less time here. Why more time there? Because it's slower here, and here it's faster. So we're going to turn that into curvature in a second, but more time here, less time here means that it's, if I were to graph it, okay, unfortunately, we're going to have to do y along the x-axis, but at y equals h, there's a high probability right? Probability of finding it at a specific value of y. This is probability, not momentum, right? And here, it's a lower value at 0. So it's probably going to be some function like this. And we could probably actually come up with a cool way of graphing that. Like we can do it as like an inverse proportion to the velocity or something like that. Either way, I just wanted to qualitatively say, well, there's a higher probability. It's like, say I didn't know when I dropped it and I wanted to randomly choose a moment in time. Well, it's more likely I find it up here than here because by the time it's falling, it's spending more time here and less time here. That's not the best way of looking at it from a classical perspective because I do know, right, in the classical, it's known where it is. It's not a probability. I know for a fact that v of y is going to be g times t, right? Or sorry, v of t is going to be g times t, right? At a certain specific time, I know that it's just the acceleration of gravity times the time. I know that. I know where it is and I know how fast it's moving. But the point is to go to the quantum worldview, we wouldn't look at it like that. We would look at it as a probability that it has more chance of being here than here. So this is not the answer. We need to figure out the quantum version of this. And we use this to do that. Kinetic energy is this. So this is the big deal equation you guys already have in your notes or should already have in your notes. If you don't, please write it right now. Let's do a little analysis. If kinetic energy is positive, and you might say, isn't it always positive? Not in the quantum world, it's not. You can have negative kinetic energy, which makes no sense classically, but this is how the universe works. The universe actually works in this strange way. And we just say strange just because like we want things to be in little boxes, but they're not. So we have to make this strange. This is strange. This is too simple. Or this is too predictable. Let's make this simple, right? So what does that say? Well, if psi is positive, that means the curvature is negative because positive, negative, negative makes a positive. Ooh. And if psi is negative, then curvature is positive. Well, what is curvature? So, for instance, if I did like large kinetic energy, here, let me do this on another slide. So if I have large kinetic energy, in other words, fast, but we don't really want speed, right? So, or potential energy is low, right? Versus small kinetic energy, where potential energy is high. Because remember that delta KE still equals negative delta PE. This still is a foundational principle that E total is still equal to KE plus PE. This is still foundational for all of physics, right? All of physics still operates on this. Large kinetic energy means large curvature. What is curvature? Curvature is how fast it bends. So like tight, skinny, like this, or like this, or like this, or like this. It's going to be one of those like four shapes, right? In fact, I can draw this one a little tighter, right? Like that. Small kinetic energy means small curvature, which means wide. So a big wide curvature like that, or like that, or like that, or like that, right? Wide. See how easy that is? What's amazing is that it actually connects to this idea of like wavelength. So this is a wave, a smaller wavelength means more energy, right? So it connects to that concept that you might already have familiarity with, right? So let's do an example, right? So for instance, right, the free particle right, has constant curvature, constant velocity, therefore constant free particle, meaning no force, which means constant velocity, which means constant kinetic energy, which means constant curvature. So, like a sine wave, a sine kx minus omega t, like we've done, right? Now, you might say, okay, haven't we talked about how this is mathematically correct, but maybe not physically correct? We may or may not have talked about that in class yet. The point is, mathematically, this is a free particle, like or cosine or plus. You can do just adding them. The real answer to this is a e to the I kx minus omega t is the general wave function in the complex plane, which is a math tool that works. It works best to model a free particle. The point is the curvature is constant, right? It's the same curvature. But notice how, notice this, right? Kinetic energy is positive, correct? So what happens? Well, if I have the x-axis here, right? And here's like the y, here's the psi axis, right? Psi of x and x. When psi is positive, the curvature is negative, negative curve, right? Do you see how it's curving down? When it's curving back up, right? This is positive curvature, but notice that it's a negative psi. That's not coincidence. And then when it's positive psi again, it's negative curve. Ah, so let's go back to this slide. So when I have positive values for x, sorry, positive values for psi, the curvature is negative. When I have negative values for psi, the curvature is positive. This means it always returns to the axis, always comes back, which means it does what? It oscillates like a true wave. What's interesting is that if we look at the other possibility where kinetic energy is negative, and I'm erasing that because we're really just going to want to know this. This is called a classically forbidden. Classically forbidden, meaning that in our, balls move like little ball objects moving at velocities, we can never have negative kinetic energy because 1/2 mv squared, it will never be negative. You can't have an imaginary velocity. So that means if I have positive curvature, I'm sorry, if I have positive psi, I have positive curvature. Because if that's positive and that's positive, that negative sign is what really causes this, doesn't it? This you need to know tremendously. And negative psi means negative curvature. So what does that mean? Well, negative psi, positive curvature, positive psi, negative curvature. Let's do the equivalent over here. Positive psi, positive curvature means it curves up. Negative psi, negative curvature means it curves down because it's negative, but it's curving down, more negative. And here it's positive, but it's curving up, more positive. So that means these go away, typically exponentially. And we're going to show that if we haven't done that in class yet, we're going to prove that the answers to these are always exponential. This is going to be e to, we call it ax, and this is going to be negative e to the ax. Now, this could also be this way as well, right? So we could have e to the negative ax or a negative e to the negative ax, which means it could exponentially decay or grow. And whether it does decay or growth will depend on the specific situation at hand. But it'll always be this, right? It'll either oscillate back and forth, or it's going to exponentially decay or grow. That's pretty much like a summary of wave functions. They do something like that. It's pretty remarkable. So, for instance, let's do our gravity. This will be the last thing we do, right? F equals mg. So this, the whole point is a force gives a potential energy. And the potential energy gives a wave function. Done. And the wave function gives you the kinetic energy, momentum, probability of where to find the particle, right? So probability, this squared is the probability of finding the particle. So there's no certainty of where it's going to be, but there's a spread of probabilities. So for instance, let's apply this. So if I drop an object, it's going to have zero kinetic energy here, which means no curvature. Up here above it, we have kinetic energy, it would be negative, which makes no sense classically, but we need to take that into account quantumly. And here we have kinetic energy equals large or maximum as it hits the ground. And let's say we have an infinite force at the ground, which means the potential energy is infinite. So it can't pass through. We have this upward force of the ground that just smashes it. So what does this look like? Well, let's graph it. So first of all, let's graph the potential energy. And I guess we want it as y, although it doesn't really matter if we choose x or y. You can choose any coordinate you want. You can call it banana, but I'm going to call it y, right? And y on the x-axis I know is weird, but we're going to start at y equals h and end at y equals 0. So the potential energy starts off high, goes to 0, and then goes like that. It's a linear potential energy, right? Potential energy equals mgy, right? So what's the kinetic energy look like? Well, here the kinetic energy, and here's the total energy. The kinetic energy is just the difference, right? If we lose potential energy, we gain kinetic energy. So the kinetic energy is just this gap here. So here the kinetic energy is 0. And here the kinetic energy is large and large. So what we can do is sort of graph the kinetic energy in pink like this, right? Kinetic energy of x can be like that. So the whole point is the curvature is small here, and then if it kept going, obviously that's what I'm getting at. The kinetic energy would be negative because technically the potential energy grows here as well, right? And we're just going to say it stops at 0, so I shouldn't have drawn that. So here the kinetic energy is actually negative, which is interesting. So let's do all of this using this, and this. That's it. Using these two slides. That's it. So how do we do this? Well, I have let's do it in orange. Psi of y is the curvature, right? So the curvature is the kinetic energy. And I know where kinetic energy is normal, like positive, here kinetic energy is greater than 0, here kinetic energy is less than 0, and that's here, right? So here kinetic energy is greater than 0. So where is it large? It's large at 0, right? So I have a large curvature here, and the curvature, so this is y equals h, the curvature kind of widens out dramatically like that. It starts to get really wide and then narrow. So here it's high kinetic energy and oscillating. It's oscillating because kinetic energy is greater than 0, which means if I have positive psi, I have negative curvature. I have negative psi, I have positive curvature. So it just oscillates. Here it gets really wide, low kinetic energy. And then it oscillates. And then what happens? And then it decays down to 0. Because here I had low kinetic energy. Here it's oscillating for that reason. Here I had high kinetic energy, and here I have kinetic energy is negative, which means it decays or exponentially grows. And I think it makes more sense that the probability would decay up here, because mathematically it could be either. You're either going to get it to exponentially grow or decay, but if it grows, then the probability would grow. And clearly I have low probability up here. So I have to have a low psi squared of x up here, right? Which means it's going to decay. Pause, let that make sense. There's a few ways I could have drawn this. I could have had it decay from above. It doesn't matter because I just do psi squared. So I'm just getting the shape, right? So this is just the shape of this graph. Pause and see if that made any sense. I hope that made sense. I'm just applying these principles, right? This and this to just drawing this. There's actually a name for this function. It's called the Airy function. You don't have to know that, but the Airy function has this shape and is the solution to Schrodinger's equation for this specific type of constant force, right? So this is the constant force solution. Anytime you have a constant force, the graph is going to look like this. That's what your psi squared, or at least in shape. In general shape, it's going to look like this. It gets high kinetic energy, high curvature, low kinetic energy, low curvature, and then negative kinetic energy, decay. Isn't that cool? I think it's so cool. So it shouldn't exist here, but it can, right? And then it goes faster, 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 faster. That's it. Welcome to the weird world of quantum wave function.